Good morning, good evening, good afternoon, everyone. Welcome to the second day of this online conference. And this morning, I'm going to talk about the basics of modal testing and analysis, because I think it's some basics ground that could be useful for you to know, to understand some of the other talks. So what is it? So I talked quite a lot about frequency response yesterday, and I'd like to go back to this if I can. I don't manage to get to the next slide. Okay. Is that okay? Can you see properly? Yeah, okay.
Claudia, for some reason,
yes,
you have your main slide on the left, and then you have a preview of the next slide on the right. It's fine, but
presenters view, isn't it? It's like, so it's okay, like so you've got two screens. If you've got one screen, you don't want that view.
Okay, it's because I have two screens, and apparently I'm sharing not the proper one.
You're sharing the wrong one.
Okay, so how do I do this? It was automatic. I was hoping I could, yeah, okay, so it's not working the way I thought it would. Can I do this? Okay, sorry for this. So I was talking about frequency response. So yesterday I mentioned it quite a few times, and I said it's a response of a vibrating structure as a function of frequency, and that's why it's called frequency. And what is it exactly? It's the ratio of the output response of a structure due to an applied force. So here you put a force, an input force, you will measure the output, and so you measure both, and you can basically do the ratio between the output and the input. The output can be measured as a displacement, as a velocity with a laser vibrometer, for example, or as an acceleration with an accelerometer. For the input force, we use a sinusoidal force whose frequency, so that the rate of oscillation is varied. And for example, here we will increase it linearly with time, but whose amplitude is kept constant. And then we record the response as a function of time. And what do we see? This is the response. And you see that for some, so here you have to imagine that this is the axis of time, but it's the axis of frequency as well, because we are increasing the frequency. Okay, so we excite with the sinusoidal force, and we increase the frequency. So here the frequency is increasing. And what do we see is that you can definitely see that the response of the structure can be very different depending on the frequency. So here it's a very low response, and then this is much bigger. And so you can see that the frequency response will not be constant. Okay? You have, depending on the frequency, the amplitude of the response can be quite different. And when we have like a very, very large response, that's what we call a resonance. So now if we divide the plot of the amplitude as a response, we can actually plot the amplitude as a function of frequency. This gives you the red plot, okay? So you can see that here, the response is much higher than it is here. And here you have a peak, which you don't have here. You see here, there is almost nothing, okay? So what you can see here in the time domain, we can transfer it into the frequency domain, because basically here, the frequency is increasing with time. So we have an equivalent between frequency and time. So this is a curve you have seen in my talks yesterday, in Colin's talks, I think in Jim's talks, and that you will see probably in other talks during the week. So the frequency response doesn't change if the position of the excitation and the response are swapped, okay? So you will get the same frequency response if I just swap. I put the output response here to measure it, and I put the input force here. I can see the chat flashing back. I can't see. So Tim, if you don't mind doing the moderator again, and if there is something unclear that I should address right now, thanks for letting me know.
Sure. There's just some people who apparently don't hear you as well. Maybe your internet connection is not so good, but me and George, we hear you fine. So so we don't know. So perhaps some people don't hear you very well due to your internet connection, or maybe it's just one person. We don't know.
Okay.
But if there's a, Blaise says it's fine there. So if there are any questions, I will
okay.
interrupt you.
Okay, so yeah, so you get the same frequency response if you invert the two, you swap the two position back and forth and response. So I told you that when you have a peak, it's called a resonance or a mode. And so here we can identify in this frequency range, we can identify 4 modes for this rectangular plate excited at this corner. Yes, first resonant, or it could be natural frequencies. They can be called eigenfrequencies. There are different names, but it's basically the resonances of the system. So we can look as well at the mode shapes. So that's the deformation pattern on the structure at each one of these natural frequencies. How are they obtained? They are obtained experimentally by placing a large number of evenly distributed accelerometers on the plate and measuring the amplitude of the response of the plate with different excitation frequencies. So if we were to dwell at each one of the natural frequencies, we will see a deformation pattern that exists in the structure. Okay, so here at this mode, by actually measuring the response on a grid over the plate, you can see that this is how the plate deforms at this frequency. This is mode 2 for this frequency, mode 3 for that frequency, and mode 4 for that frequency. So here I basically explained how these measurements are done with sinusoidal shaker. Okay, and then you increase the frequency through time. But there is another way to do it, and that's what we are actually using, because we talked about it quite a lot yesterday with impact hammer testing. So the measurements can be made with a shaker with frequency swept or with an impact hammer, because the FFT of an impulsion is a very broadband spectrum. So you have a large range of frequencies which are thus, which is thus excited. So you have 2 ways: either you sweep the frequency, or you just give an impact. And basically an impact, especially the more sudden it is, the more broadband in terms of frequency it will be. So you can actually excite a large range of frequencies just with one impact. The input excitation frequency range is controlled mainly by the hardness of the tip, which is selected. So the harder the tip, the wider the frequency range that is excited by the excitation force. And the tip needs to be selected such that all modes of interest are excited by the impact force over the frequency range, which is considered. So usually if you want to go to high frequency, you need a hard tip. But then, of course, if you hit the bridge, it's kind of fine, a hard tip. If you want to hit the top plate or the back plate, then yeah, the hard tip, you may destroy the varnish. So you have to be more careful. And I have this in mind when in Oberlin at some point, the Betz was there and George was in charge of doing some model testing. And he was with his hammer and being very delicate because he was worried. And you had the 2 curators of the museum being like this, you know, and like seeing the reflection, making sure that there was no indent while he was tapping on the plate. It was pretty stressful, I think, to make sure that nothing is damaged. but on the bridge, it's kind of fine. And so we usually use hard tip. Actually, what works very well is when you put like a little plastic cap on it with plexiglass. That makes it very hard and flat, but doesn't damage the violin as much as the metallic hard tips that are usually distributed with such small impact hammers. Let me go back to this figure. So here you have different curves in kind of bluish curve. That's the response of the hammer. So you can see that it has a lot of frequencies, but at the same time, the energy of the hammer is definitely much lower at higher frequencies than it is at low frequency. The black curve is a frequency response function, so the response divided by the input. And then this red curve is called the coherence. So what is it? It's when you do such a measurement, you can't do it just with one tap. Usually you do a few taps and you average over the tap. And the coherence will tell you whether when you average things which are coherent, okay? So making sure that you are not averaging potatoes with leeks, for example, you know. So you can see that up to these frequencies, the coherence is pretty flat and really good. And above this, the coherence starts looking very bad, which you can see in the measurement as well, very noisy. And this is happening because you see that the power of the input is getting very low. So you don't have enough energy. And because of this, you have a lot of noise. And the noise is, by essence, not coherent. So when you average noises and you get a lot of crappy things. So that means that your measurements cannot be trusted. Now, this is with a hard tip. And I think that there is a mistake here that shouldn't be 200, but 2000. And then you can see that with the hard tip, the input power spectrum is you see it's rolling off much more slowly. So that means that you can have higher energy input for a larger band of frequency. And that shows you then a very nice coherence up to 2000 Hertz. Okay, so this is, I'm discussing about this because there are some measurements which are commonly done by makers who want to start trying to do some measurements, and that's the basics of how to interpret the curves you will see on the graph. So always check the coherence to see that your measurement is valid. So what happens after that is we want to estimate what we call the modal parameters. So for a resonance or a mode, it corresponds to one single degree of freedom oscillator. And one single degree of freedom oscillator has three parameters. The omega here, or F, which is the frequency of this mode. You have the amplitude, okay, so the height of the peak, and you have a quality factor or damping zeta, which is related to how narrow the peak is. And so from a frequency response, you can deduce the three modal parameters for each of the modes or of the resonances. Now, what is a single degree of freedom oscillator? It's the simplest oscillator, a spring, a mass, and a damper. It has a stiffness coefficient, K, a mass, M, and the viscous damping coefficient, C. And this is one resonance. The frequency is omega, or 2 pi f equals the square root of K over M. The damping depends on Cf frequency, and it's inversely proportional to the width of the peak in the frequency domain. and proportional to the decrease of the signal in the time domain. So if you look at the response, so for example, you hit a mass like this to make it oscillate, okay, on the spring, then you record the movement of the mass as a function of time. You will get damped oscillations at the resonance frequency of this system, which is the square root of k over m. And it's damped because of this viscous damping C. Okay, so here you get the period and the rate of decreasing is linked to this damping zeta. If you look at it in the time domain, in the frequency domain, it's a peak, and depending on C, and therefore depending on zeta, you have peaks with different widths. Okay, so with a zeta equal to 20%, so a lot of damping, the peak is basically almost disappearing, and we barely see the resonance anymore, very wide. And if you have a zeta of 0.1%, so very, very small damping, which is what you could find for string, then you have a very sharp peak. So you can see as well that the amplitude of the resonance will depend on the amplitude that you see of the peak is depending on zeta as well. Okay, so basically what happened is like if we have a physical structure here, so here it's just like a bar or a string, or okay, you can see different resonance frequencies. And here we have like mode 1, mode 2, mode 3, and usually have a very high numbers of modes. We can look it in time domain. So that's the response if you excite the structure, that's a complex response of it. It can be decomposed as the response of, for the first mode, second mode, a higher frequency, so you can see it's, yeah, the periods are smaller. And then third mode. So this is in the time domain. So basically the time response is a linear combination of these responses. And you can see it as well in the frequency domain. So in the frequency domain, so the two are linked by FFT, fast Fourier transform. And you can see the modes here. You see the 3 peaks corresponding to the 3 modes. And you can decompose as 3 individual peaks that you sum. And that's, we are not going to talk about it. It's just like basically telling you that it's actually 3 oscillators. Each of them can be modeled as a mass on a spring with a certain viscous damping. Okay, so any physical structures can be decomposed as a sum of single degree of freedoms oscillators, so as a sum of masses and springs and viscous damping. And so you can see it. So any response of a physical structure to a certain excitation is a linear combination of the responses on the different modes.
Testet hur det funktionieren. Weil da kann man einen Audio-Test machen.
Sorry? Okay, so I don't think it was interesting. Is that clear? Do you need any more explanation? It's okay. Okay.
Claudia?
Yeah?
The different modes have different effective masses and different effective stiffnesses and different dampings, right?
Yes, yeah. Yes, indeed. Because those, I mean, it's basically mask, just so you can get the proper resonance frequencies with the proper amplitude and proper damping factor. So yes, it will all be different masses, stiffnesses and damping.
Terry asks, how did you define the coherence in the previous slides? So what it is exactly, maybe.
If we go back here, well, it's a computation where basically you look at how similar the measurements are from one to the other. It's not easy to explain, so, but it's basically, usually if you use a software to actually measure this, the software will provide you the coherence. And you have to make sure that you look at it to know in which frequency region your measurement is valid. So It's not something you keep at the end. At the end, you just keep the measurement, but you should look at it when you actually take the measurements just to make sure that you are doing the correct measurements. It shows you as well, like for example, with the hammer, it's very easy sometimes to actually not hit at the proper place, at the same place, just because your thing is a bit moving, and so the coherence shows you as well that you are hitting in a very systematic way as well. So for example, if you hit manually, sometimes if you don't hit properly, you can have a bad coherence even with a hard tip starting at very low frequencies. And that means that there is something wrong with your measurements, that you are basically not hitting in a consistent way. So you are measuring different things. And basically the coherence wants to show you that, hey, wait a minute, here you are doing nonsense. Okay, if the coherence is bad, it's because you are trying to average things which are not similar, and that doesn't mean anything. You get a curve, but what does it mean? Okay, so it's important to look at the coherence to make sure that your measurement is valid. It can still not be fully valid because the coherence is good, but at least it's definitely better if the coherence looks good. And you definitely should discard your measurements if the coherence doesn't look good. So like, for example, with a coherence like this, here, you should discard the measurement after this frequency. So then if you use it, you only look at this area. Does that answer the question?
Is it clear, Terry, for you?
Sorry?
I'm asking Terry if it's clear for him. Yes, he understands. Okay.
Okay. Okay, so I talked about mode shapes. Now I'm going to talk about operating deflection shapes. So here, so this is the frequency response of this rectangular plate. And if we are at this frequency here, we are basically at the frequency of the resonance. Okay? And we can see that if we decompose these two modes into 2 degrees, 2 single degrees of freedom oscillators, it's the blue curve for mode 1 and the red curve for mode 2. What we can see is that if we are at this frequency here, the amplitude for mode 1 is very high because we are at the resonance, and the amplitude for mode 2 is very, very low. So that means that if you excite the structure at this frequency, you basically only excite mode 1. Or mode 2, you will excite it so small that the contribution is going to be very, very small. So what you see here when you actually look at how the structure is vibrating, which is the operating deflection shape, this will actually correspond to the mode 1 shape because we don't have much contribution of mode 2. Okay, so here the operating deflection shape is equal to mode 1 shape. Now, if we move to another frequency, here we move to this frequency, which is the frequency of mode 2. Here, you can see that at this frequency, we will excite very strongly mode 2, and we will barely excite mode 1. So here, at this frequency, the operating deflection shape is going to be the shape of mode 2, or very close to. But now you can see that if we actually excite somewhere here in the middle, you can see now that you will excite the 2 modes with really similar contributions. And so here at this point, how the plates will actually move and deform and vibrate is the result of mode 1 and mode 2 behaviors. Okay, so the operating deflection shape here is going to be the linear, a linear sum of the mode 1 shape and mode 2 shape. Okay, so the operating deflection shape is what actually happens at any given frequency. The mode shape is what you have if you could only excite the structure at its resonance. So when the peaks are well separated, you can actually measure the mode shape because you know that the operating deflection shape at this frequency will correspond to mode shape. But when you are higher frequency and the mode starts to what we say overlap, then you will never be able to measure the mode shape. You will only measure operating deflection shape. And the mode shape, you only get them through softwares, which will be able from the operating deflection shape, be able to get the mode shapes. Does it make sense? Okay. So what is modal analysis? So it is, it's a lot of text, but because also then if it's put on online, then you can go back to it and have time to read it. And so you have like something which stays with some explanation. So it is the process of determining the inherent dynamic characteristics of a system in forms of natural frequencies or resonance frequencies, eigenfrequencies, damping factors, and mode shapes, and using them to formulate a mathematical model for its dynamic behavior. It's based upon the fact that the vibrational response of a linear time-invariant dynamic system can be expressed as a linear combination of a set of simple harmonic motions, which are single degree of freedom resonators, oscillators, which are called the natural modes of vibration. And each mode is described in terms of its modal parameters, natural frequency, modal damping factor, and the mode shape. The mode shape may be real or complex. Each corresponds to a natural frequency, and the degree of participation of each natural mode in the overall vibration is determined both by properties of the excitation sources and by the mode shapes of the system. So I'd like to finish this by talking about where do modes come from. So yesterday, I showed you already this video, and I want to show you another video to show you the effect of the boundary conditions and what they imply about the reflection of the boundaries. So I just, in case some people were not here yesterday, I will play this again. So you can easily see the wave traveling on one way and then being reflected at the other end. And as you can see, the reflection is going opposite sign, because basically this is a fixed end. That means that here, this bar here cannot move. And because of this, the reflected wave is going the other, is going underneath. So at this end, the inwards wave and the reflected wave do cancel because of the fixed end.
Two questions, Claudia. First, yeah. I want to quickly interrupt because your video is not always so good. So I'm not sure if everybody saw the movement of the video. So perhaps you could do the video again. And then also Terry asks, do we assume a violin is a linear time invariant system?
Yes, sir. In terms of vibration, yes, it is. We are talking here about the body mode. Yes, any structure is the vibration of the body is can be decomposed linearly into different modes. What is not linear in a violin is the excitation process. Okay, the stick-slip motion of the bowed string. This is non-linear, but the response in terms of vibration of the body, this is linear. The vibration of a structure will become nonlinear if you really excite it at very, very large amplitude. You never achieve such amplitude with the violin. Okay, so at the range of excitation amplitude it is excited, like normal bowing or normal heating, you are still in the linear domain. To reach non-linear domain would mean actually breaking the violins into pieces. So. Because you would excite it so badly that it would just be destroyed. If otherwise, you can Google St. Mary's University And you will probably find the links to the animations, or I can find them for you and post them. But what is important to see is the fact that it's actually going back down the other way, the other sign. Oops, sorry. So now what happened here? And I think this is was more struggling with it when I was a student, just because you feel like, well, there is nothing there, and so why is there a reflection? You know, because here you can feel intuitively that because it's fixed, it can't really continue. But when it's just kind of what we call a free end or an open end, you would feel like, why is it reflecting? And but it is as well. But now you see that the wave is traveling, it doesn't change sign. You see, it still stays above. Okay. So you can see that the boundaries have a big effect on how the waves reflect. And so it will have a big effect on which wave will actually survive when you go back and forth, like as different reflections. And so it has a big effect on the resonance frequencies. So a structure with different boundary conditions will have different resonance frequencies. And so when you measure your free plates of the violin, if you actually use the different conditions, like for example, George, Stepani has designed this new device to actually make pinned edge conditions, you will get different mode shapes and different resonance modes. So talking about the resonances of the system, you really need to define this system properly and how are the different boundary conditions and everything, because you change this and of course you will change the modes. And so this is the free end is basically what happens with musical instruments, with not musical, with wind instruments. You know, you have the vibration into the air column inside the instrument, and at the end of the pipe is open. You feel like, well, it's open, it's still air. So why would it be a reflection? It's because the pipe is open into like a tank of atmospheric pressure. And because of this tank of atmospheric pressure, that means that the acoustic pressure has to be equal to zero or almost. And so that imposes a node at the end of the pipe, and that imposes to have reflections within the pipe and to have therefore modes. And that's how it works, because if there was no modes, no resonances, then you wouldn't hear any notes. So different boundary conditions, as I said, lead to different modes, mode shape, mode frequencies, everything will be different. And that's why there is no direct link between the modes of free plates and of plates when assembled in a violin. And the only way to basically is what like Colin is doing, is trying to numerically simulate different like wave stiffness. So he goes from the free plates and then he adds waves progressively more and more until it's assembled violins, and then you can follow what's happening. So the free plates, when you thin the edges, you decrease the mass and therefore the resonance frequencies go up. But with fixed edges, what matters here is not the decrease in mass, but the fact that it's more flexible at the edges. And so the resonance frequencies will go down. I showed you some videos yesterday about vibrating strings and square plates. I'm talking about some violin and viola plates here. So here, that's a viola. You have the mode 1 for the top and the back and the top. Here, you have all seen this. You have the mode 2 X mode for back and top for violin, and the mode 5 for back and top. So it's actually, what you see, it's actually getting a bit more complicated for the top. You see, the X is not such an X for the top. And that's because of the presence of the F rolls, which makes the plate more flexible to bending on the short axis, and the bass bar, which makes the plate less flexible to bending on of the long axis. And so because of this, the modes are not exactly the same for the top that they are for for the back, the mode shapes. And then we can look at the modes, like Colin showed this yesterday. We can look at the mode of a full violin body this time without neck and sound post. And so here the body is complete, and we only look at the modes at the operating or the mode shapes of the top and the back. And on the left-hand side, you have the measurements made by Colin on a real violin, made by George on a real violin. And on the right-hand side, you have the simulations made by Colin on a violin-like shape box. And you can see that even for a very simple model of something which looks like a violin, with not the complication of the C-bows, and you can see that the theory predicts quite well what's happening in a real violin. So this is A0 mode, which will lead to the A0 mode, because of course there is no neck and sound post, and that's why it's not the frequency that you are used to, where we see the breathing mode with the top and the back moving on opposite directions. And we see for the B1 minus with some bending implied, B1 plus, and then the CBR. And we can see the patterns being well reproduced with the numerical models. But so here I wanted more to use this as an illustration of what I've said before, where now you should be better understanding what all these mode shapes mean and what they are related to. So that's basically how the body vibrates if we could only excite it at this frequency without any contribution to other modes. And I think I'm done. I'm happy to answer questions. Yes, Dimitri?
My question about your very first slides, when you showed just a rectangular plate and with the positions of output response and input response. My question is that I assume it will be important where do you put the output response, because if it's on the modal line, if it's on the nodal line, and will you have to have some kind of correction on that? And when you do this kind of test on violin too, how is it treated?
I mean, you will always be on a nodal line of a mode, but doesn't matter because you will not be at the nodal line of all modes. So it depends on what you want to do. You know, if you just want to measure the frequency response, you have to know that the frequency response is only relevant to that measurement point. Okay, so you can't use this measurement to actually extrapolate what's going to happen in another point of the structure. So you have to use a measurement point which is meaningful. Okay, so for the violin, we usually use at the bridge because we feel like, okay, the string is actually exciting the bridge. So we do it at the bridge notch because that's basically where the string puts the energy and into the violin body, and that's why we measure it there. And then, yes, you will be at the node of some mode, and that's why you will have troughs. You have resonances when you are when you have a very big response. But if you are on a nodal line, you will be in a trough. Okay. Now, if you actually want to do, I don't know, if you want to show that there is a mode happening, and then of course you just want to take a few measurements, you have to make sure that you are not on another line, otherwise you will not see that mode. But that's a different question. Okay.
Yep, thank you.
It depends on what you want to do, but if you want to grab the response of the structure at different frequencies, then it doesn't really matter where you measure it, as long as it makes sense to your purpose. Okay, why do you want to measure the frequency response? Okay, so it's more this question that will tell you where to do the measurement. And then yes, that for sure any places will be correspond to the node of at least one mode, that's for sure, but doesn't necessarily, it's not necessarily a problem. Okay. What would be a problem, for example, is like if you want to see, you want to be sure that in your frequency response, you want to see a certain mode because you want to actually look at this mode a bit more. Then of course you have to measure somewhere where you know that this mode doesn't have another line. Okay. Does it make sense, what I explained?
Yeah, for sure. It's just like the same idea, like we check the free plate modes, and it matters where we put the foam pads between the speaker and the plate, because I was thinking just this output and input response technique looks so profound that I was thinking that, and like people like yesterday we saw from the Cremonese acoustical laboratory, people are using it on historical instruments. So I was thinking that maybe it just gives us a super objective picture, but yeah, of course we have to keep in mind the weight of this output responses thing and where we put them. So it totally makes sense. Yeah.
Okay, there are some more questions in chat.
Yeah.
First, I'll ask Terry's question. Why in this PowerPoint is the top and bottom plate that you showed that have the same frequency for the same mode? Are they tuned to be the same frequency, or?
For the last slide.
I think the slide where you showed the actual wooden plates with the modes and they had the same frequency, or?
No, they didn't have the same frequency.
Actually, yeah, from the picture you show for the same mode, the top and the bottom plate, they have the same frequency. But
No. I mean,
can you show the last slide?
The last slide, yes, because the last slide, it's not the frequency of the independent plate. It's not the modes of the independent plate. It's the mode of the full body. It's the mode of,
okay, I see.
It's a complete body without neck and sound post. And I tried to explain it, it was probably too fast. I explained that we are actually looking at how this mode shape for the full body, we only represent it on top and the back. Okay.
So it is like the top and the bottom plate, they put together.
Yes,
so
they are together.
Like okay.
With ribs. Okay. The thing which is missing is the neck and the sound post. Okay.
Okay, but individually, the top and the bottom plate, they should have different frequencies, even for the same mode.
Yeah. Here we are looking at the mode of the complete body.
Okay, I see.
And to actually look at it, we represent how the top and the back plates do vibrate for this mode.
Okay, I understand.
It's the mode of the full body.
Okay, great.
Okay, Rie has a question about the open boundary conditions.
Yeah.
He asks, with the opening of the mouth or the F-holes in violins or guitars, does that then equal an open condition where the wave is reflected differently?
No, because here we are not. Well, I was talking about the open conditions more like for a pipe, when you actually create a standing wave inside the pipe. Okay, and so at the end, basically you have a tank of atmospheric pressure, and so the wave inside the pipe is going to be reflected. It's actually a bit more complicated like this because there is radiation. If it was fully reflected, we wouldn't hear anything, okay? Because basically the wave would be stuck inside the pipe and we wouldn't hear anything. Okay, so of course there is a bit of leaking, okay? And so it's not exactly at the end of the pipe that the condition is acoustic pressure equals 0. It's a bit further because there is some leakage to some extent and radiation. And to actually have a bell at the end of the pipe changes where it actually goes to 0 and makes the fact that it actually radiates more efficiently than if there is no bell. Okay, so the bell is basically trying to make an adaptation between the pipe and the the tank of atmospheric pressure. You basically go more progressively from a very small pipe to something which is completely open.
I think the question is more in a violin. When you have your vibrations, they start at the bridge, they travel outwards. When they meet the sound holes where they are cut, that they bounce back like an open condition, so they bounce back up. While if they meet the edges where they're fixed, there they bounce down. I think that's what
it will affect how the waves are traveling and back and forth, and that will affect the mode shapes. Yes. And so, yes, that will affect the mode shapes. And so, if you didn't have the F-holes, the mode shapes would look a bit different.
Claudia, will George Stepani talk about his nifty finger thing for holding the plates when he does his tap test? It's not a free plate anymore. It's a restrained up and down, and he can bend outward and so on. Sometime this week, will he be described? Anybody describe this?
The pinned edge system. I don't think it's planned, but I don't know, George. Were you planning to?
I'm here. I'm not talking about it at this conference, but I am talking a bit about that at the VSA thing.
Oh, the suspense.
Yeah, but you're right. I mean, when you look at say a violin top as a free plate, and then you cut the F-holes, you don't see much difference in mode shapes until above a kilohertz or so, and but you do get a change in frequency. And when you look at it with the so-called pinned edge system, you see differences much earlier. And what it's about is when in the free plate, when a half wavelength becomes commensurate with the distance between the F-holes, then you get that area starts to behave independently. You get what's called localized modes. So I think that's part quite a lot of the explanation as to why there are differences. So the F-holes below a frequency, they just reduce the overall elastic modulus, and at a higher frequency, the boundaries start to affect the behavior, because a wave arriving at it simply reflects back instead of crossing right over. So a long wavelength, a large wavelength, simply ignores the F-hole. It goes all the way around it and across it. Does that help?
I assume
I mean, it's taking
it better.
a rather specific question about modal behavior rather than the generality of how you do it and what it means. But I think it does highlight something. You said, well, I'm going to do a modal analysis of this. Well, actually, the particular chosen boundary conditions for that measurement are rather critical. So free plates are easy because it's the most easy situation to replicate, or whatever, or if you hold the plate between your fingers or sit it on bits of foam, it's all much the same thing. But if you start to look at another boundary condition like restraining the edges, it becomes a lot more difficult. It's nearly impossible to keep anything still. But what it does is it's much more like the behavior of the assembled instrument.
I'm showing here the picture for people who have no idea what you're talking about. The picture of the system that Marty and George are discussing, where you actually pinned the edges here between little two clamps, and was used here to actually measure to make the modal analysis of this plate in a pinned edge conditions. If you want to use a picture to illustrate what you're saying, George.
Yes. Well, the idea is that we're trying to just remove one degree of freedom, that is the vertical motion at the edges, and we're trying to minimize the clamping and resistance to the perimeter spreading and shrinking. Of course, it's impossible to do that, but it's a question of to what degree do you manage to achieve that state. And another reason is, of course, because in the finite element modeling, this is a very clear-cut condition which you know, somebody working with FEM can model. And
yes,
the
and
information is.
Well, sorry, you didn't mention as well that you designed the system because you have the feeling that the plates, when they are assembled into the violin body, they are closer to a pinned edge condition because of the ribs than they are to free plates conditions. And so you feel like measuring them this way is probably closer. It should give you something probably closer to how they behave when they are assembled.
Indeed. But in fact, the assembled instrument is a very complicated set of boundary conditions, because in some ways it's partly like a pinned edge, it's partly like a free plate, and then you have the you know, each plate contributes to the boundary conditions of the other, so therefore the strong coupling of the plates. But conceptually, it's quite simple. And I think when you look at the different mode shapes that you get with the free plate and the pinned edge, it starts to shed light on why they behave in a particular way. But anyway, it wasn't the topic of this talk, but I think it is relevant to say that when you decide to do modal analysis, the boundary conditions are important. So if, for example, you want to know what a building might do in an earthquake, well, you make your a model, a scale model, and you put it on a table that kind of maybe shakes horizontally. So that is the boundary condition that's relevant, whereas taking the model of the building and suspending it from rubber bands in free space isn't relevant to the problem. Does that make sense?
Yes, it does.
Yes. Marianne asks a very good question, but with a complicated answer. So there is no correlation between free plates modes 2 and 5 with the body modes B1 plus and B1 minus, question mark.
She should listen to Colin's talk.
Colin answered that yesterday.
Yes.
Colin actually explained that in detail yesterday.
Yeah.
And although it's a very seductive thought to think that mode 5 becomes the breathing mode, it's actually incorrect. It's actually imagine the whole plate bouncing up and down on very soft springs. And as the springs become harder, then the breathing mode emerges, and it is not related to the mode 5 shape, surprisingly.
So sorry, I had difficulty in getting online. What George said is absolutely right. If the plates had been hinged in a very simple way, if it had been a flat plate and a rectangular plate, in fact, what actually happens is that the bouncing mode of the thing going up and down like this, when you've got very weak coupling, turns itself into the B1 mode, B1 minus mode, and what was the original sort of the ring mode of the actual plate goes up to a much higher frequency, but they are related. They're very strongly related, but it depends on the coupling strength between that bouncing mode and the ring mode. And so there's a definite correlation between the two things, but it's not it's a rather more sophisticated one than one might think. It depends very much on the ribs. The interesting thing is that the B1 plus mode is directly related, in fact, to the X mode, to the bending mode, mode 2 of the plate. That's a much more straightforward thing. Mode 2 of the plates goes across to the bending modes. but the mode 5 interacts, in fact, with that bouncing mode up and down the ribs, if the ribs were very weak. And together, it's what they're called normal modes, when two modes interact together. And the lowest one of those then becomes the B1 minus mode. So there's a very strong correlation between the original ring mode and the plate modes, but it's not a direct one, okay? And it's understanding that really for many of us the first time. It was it was a bit of a shock to me when I realized it wasn't as simple as one that originally thought. And that's why up until recently there's been no satisfactory model for the B1 minus and B1 plus modes. But now I think we really properly understand it. That answers it, and with George and Jim's contributions. So the plate modes are all important, modes 2 and 5, exactly as Carleen actually suggested. And she didn't really quite know why, in a certain sense, except that they had much the same sort of symmetries. But what actually happens with the mode 5 is that as soon as one puts the ribs on, it stops the flapping of the outside edges, like all the modes. When they're free plates, the edges of the plates can move very easily. But as soon as you put on the ribs, quite obviously, you're going to change those modes. But there is a very strong correlation between the actual ring modes and the B1 minus coming from the ring mode and the bouncing mode together, the B1 plus mode coming from the bending modes of the plates. They're very similar, but now it's not just the plates bending, it's the whole body bending. Okay?
I might point out that this understanding of the transition from the free plates to the assembled corpus is really a very, very important step in our understanding. And obviously, the more we understand about that, the better use we can make about the information of the free plates. So measuring free plates is what we could call low-hanging fruit. It's do the easy thing first. And anything that we can learn from the free plates, any way we can use that information to make our instruments end up in a particular way, it's worth having. But logically, the thing that matters is how it behaves when the whole thing is assembled. But on the other hand, if you have only that information, that's a lot less useful than seeing how you got there. So tracking the steps towards the end result is in fact more informative than just looking at the end result on its own.